Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on mathematics, of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. All right, step on inside, and we are going to be working on some two-column proofs, mostly involving parallel lines. Some things will be already pre-filled out. We're trying to find out the rest here. Just bridge the gap, make sure we know how some of these things work. So if you haven't seen any two-column proofs with me, let's check some out right here. No triangle congruence, by the way. Nothing of that accord. It's all parallel lines. I think the first one's of perpendicular lines, actually. Yeah, it is. This one here. We are actually proving in the first one that perpendicular lines create congruent angles. So we'll check that one out, and then all the other ones are some parallel lines bits, which kind of build on from each other. You'll see what I mean when I do them. All right, so this first problem here, this proof, let's prove that two angles are congruent to each other when perpendicular lines are formed on the seams. So if I create, because this is the only one that doesn't have a drawing here, if I create two lines VW and UV and make them perpendicular to each other, they both share V, so V is the vertex of this angle here where you have U, V, W. If they're perpendicular, then they create a 90-degree angle. It's actually a part of the proof. And then I'm going to do the same thing here. And, you know, they don't say it's a part of the same figure. These can be two completely different figures like this. And it looks like S is in the middle of R and T, which are RS and RT are perpendicular to each other. And, of course, they make a right angle, which is also part of the proof. We just need to prove that these are the same thing. And you can't just say, therefore they are, right? We need to make sure to say, how did it come to be? It's 6 steps. They'll make sense. To some people, it seems like a little bit of overkill, but overkill is what's needed for proofs. To prove anything, to prove people of murder, you need overkill. I shouldn't say overkill with that. You need to make sure that that it's indisputable. So we're given that these two lines are perpendicular to each other. And as a result of that, I'm going to skip statement 2 for a second. As a result of that, that makes their measure 90 degrees. That's what perpendicular lines are. The word perpendicular was made. Someone said, and therefore I will use the word perpendicular for lines that intersect at 90-degree angles. The word was made to describe that. If perpendicular is made to describe 72-degree angles, then something's perpendicular would be 72 degrees, right? That would be the definition of perpendicular lines then. So anyway, that's the creation of the word for that specific value. Therefore, that word is assigned that value. So, okay, 90 degrees. Line ST is perpendicular to line RS is given, and because of statement 2, we can therefore make statement 4 here that measure is also 90 degrees for the exact same reason. That's what perpendicular lines are, and pardon me for the shorthand here. Okay, now statement 5 is generated as a result of statements 3 and 4. If you can observe here, both of these measures are 90 degrees. So if they both equal the same measure, then they are both equal measures in and of themselves. Now that seems like substitution to us. And I would understand if you would put that. It's actually not very much wrong to say substitution. It's just not as best as you can get of an answer. And because look, if something is 90 degrees, then something could take the place of the 90 right there in order to make that statement that you can see in statement 5 right there, right? It looks like a substitution, and I'd agree, it sure does. But what we're doing is we are comparing two expressions that are equal to each other. This is an entire expression, even though it's one term, it's an entire expression on the left side of the equation. And here's an entire expression on the right side of the equation. And this left expression is equal to this right expression that is being therefore replaced. This is what is known as the transitive property of equality, which is a substitution of an entire expression for another expression for an expression in an equation. So this is known as the transitive property of equality. The transitive property itself states if A equals B and B equals C, then A equals C. And there's no limitation on what A can represent. It can be an entire algebraic expression, something massive. And the idea is two expressions that are equal to the same expression are equal to each other. Sorry for overstating it, but it is something that is used heavily, and it's used more so in congruence to the effect that there is no substitution in congruent statements. There's only transitive property that's used in congruence for things that appear substitution-like. Okay, now the last step is the proving step here. We have to prove these two angles are equal to each other. Well, if they have equal measures, congruent. If they have equal measures, then the angles themselves will also be congruent. Congruence means equal in size and shape. Equal in size and shape for objects such as segments, angles, different kinds of figures and things like that. So these two angles are congruent because their measures are equal. That is the very definition of congruence. That's what it means. That's how it's utilized. So that's what we're going to put right there. And that is your proof. That is your proof that those two angles are equal to each other, and therefore all perpendicular lines create congruent angles. Those steps in between allow us to draw that connection. And now we can make the leap all that we want the rest of our lives. Unless you're doing proofs in geometry. Okay, let's go on to number 2, where we do have a figure right here. We have two parallel lines that are cut by a transversal. Now, some things I need to state about this. This very proof right here is the given, the information's down here. Given that two lines are parallel, prove that some angles, these two right here, SVW and RSV, we're going to prove that these two angles here are congruent. Now, these happen to be alternate interior angles. It is likely, if not just very possible, that you've already learned when two lines are parallel, then alternate interior angles are congruent. But that is a theorem. A theorem is something that can be proved. We are about to prove it. So you can't use a proof. You can't prove a proof. Oh gosh, how do I say that? You can't prove its own proof. You can't say alternate interior angles are congruent because alternate interior angles are congruent. I can't use that as a reason. That's what I'm trying to say. What you can do is use things before it to make that proof happen. Now, when drawings get more complex, like when we get, let me move down. There are 5 problems here. Like this one here, when we get 3 lines, and somewhere we might want to use alternate interior angles to kind of speed up the process, because now that we've proved it with the 2 lines, something more complex is used. That's fine. At this point, if we want to use alternate interior angles or exterior or whatever, this is now out of that one's scope. It's a little bit more difficult, so we're going to save that 4-step process time and just use alternate interior angles then. But these other ones, which is 2 lines, are their own proof. Same with this one that has a kind of more complex kind of relationship here. We might use it here as well. But the idea is here when we only just have 2 lines, and you're proving that very thing, then you can't say alternate interior angles are congruent because they're congruent. It needs to be proved. All right, so how do we prove it? Sorry about that. We're starting with the fact that 2 lines are parallel. And they're marked. That's what the arrows are for. Given. Now, there are 2 angles here that happen to be congruent as a result of the lines being parallel. They're called SVW and QST right here. Now, these are known as corresponding angles. Whether or not the lines are parallel, these are known as corresponding angles. I want to make sure that that's understood, because there are, no matter how many times I say it, heck, when we introduce it, we introduce them as not necessarily being parallel. But then we teach you that corresponding angles are congruent when lines are parallel, and suddenly people just assume that all corresponding angles are always congruent to each other. No, if lines are parallel, then they're congruent. That's what the postulate states. And that's what I'm about to be saying right here. This is known as the corresponding angles postulate. Now, why am I allowed to use the corresponding angles postulate here in this proof and not the alternate interior angles proof? Theorem. Or not the alternate exterior angles theorem, or the same side interior angles theorem? Why am I not allowed to use those? Because this is a postulate and those are theorems. What's the difference? A postulate is a statement that is just accepted truth. We believe it to be true. We believe it to be true. We assume it to be true. We accept it to be true. Such as, here's another postulate. It's actually, I think, called an axiom, but here's another postulate. All parallel lines never intersect each other. That's something that you can't really prove, especially since the lines go on forever. It's something that kind of just, it's an accepted truth that we build everything else off of. So the postulate can be used at any time here. Theorems need to be proved, though. So I can use this one. This is an accepted truth, mostly because, I mean, look, they're facing the same direction here. They might as well be the same angle. They're just translated in a different part in space. You just move the other to the other. They share the same transversal. They're along parallel lines. Okay. So statement 2 was only made, though, as a result of statement 1 existing. Without statement 1, without parallel lines, Statement 2 is not possible. Let's go to statement 3. Angle QST is congruent to angle RSV. Here's QST. Here's RSV. These two are apparently congruent to each other right here. How come? This is as a result of what's called the vertical angles theorem. And sorry for the shorthand, but this is known as the vertical angles theorem. Mr. Robinson, you just used a theorem in something that you said. Now, keep in mind, you can use theorems in previous things. And what I stated before was I'm not going to use alternate interior angles theorem to prove that alternate interior angles are congruent, because I can't prove a theorem with its own proof. The vertical angles theorem is not for two parallel lines. Vertical angles have nothing to do with parallel lines. It has to do with two intersecting lines. That is in a different scope prior to these ones. Just like how I can use alternate interior angles later in something that's of greater scope, of larger scope, out of its scope, I can use vertical angles here because this is something we would have proved in the past. That just when two intersecting lines are formed, the angles opposite each other are congruent. It can be proved, it has been proved. It can be proved, it has been proven. We're just not proving it here. Now, this one was not made as a result of statements 2 or 1. In other words, this could have been made despite the fact that either of these were ever existed. This could have been my first statement, and it would have been fine. There's a reason I made this specific statement, though, because our proving statement needs to be that angles SVW and RSV are congruent to each other. So I need to relate SVW and RSV to the same angle somewhere in a way that I'm able to. We're able to show that they're both congruent for different reasons, right? Therefore, these will now be congruent to each other, and that's our last statement. Should be the proving statement. Angle SVW is congruent to angle RSV by the transitive property of congruence that says two angles congruent to the same angle are congruent to each other. So this statement was made from statements 2 and 3. Because of statements 2 and 3, we could make statement 4. Okay, so that's what was happening there. And this is proof that alternate interior angles are congruent right there. The alternate interior angles, of course, were these two right here. That is when lines are parallel. Without this given, that is not true, or not necessarily true. Probably not true. If they're not parallel, then they're not congruent. I can say that much. But if you don't know, they're parallel. All right, talking a lot. Let's keep going. 6 steps here to prove that two lines are parallel. Okay, so this is interesting. And if you've done any of the parallel things before, then you probably know how this stuff works. We need to show that certain angles are congruent or supplementary to each other in order to prove that the lines themselves are parallel. Okay, so here we go. We're going to start with the fact that two angles are supplementary to each other. PRS and PRS and VUW. PRS, VUW. And I'm going to mark them differently, kind of like that. We're going to know which ones they are, but they're supplementary. That's going to be our given. Now, to us, these are same side exterior angles, but of course, because this is just involving two lines cut by a transversal, we are only in that scope where we can't just say that because same side exterior angles are supplementary, then lines are parallel, which is a theorem or a converse of a theorem. But we can't use it. We can use something for corresponding angles postulate. So if we can if we can relate another angle to these two to find something to draw that connection to with corresponding angles, then we can use its converse. And that's what we're about to do. We're about to prove these two lines are parallel. So here we go. If angles are supplementary, then those measures add to 180 degrees. That is the definition of supplementary angles. Supplementary angles are angles that add to 180. They don't have to be a linear pair. They just need to add to 180. They don't even have to be adjacent. They just have to add to 180. Now, there's another set of angles that also add to 180 here. Sorry, this is a result of this. There's another set of angles that adds to 180 here, PRS and SRU. Well, what is SRU? It's this guy, right here. For now, I'll give it 3 arcs because right now we don't know anything else about it. I'm just indicating where it is. Here's this SRU guy, which is supplementary to this one right here. Does that have anything to do with the fact that those two angles before were supplementary? No. This has to do with the fact that these two are adjacent and form a linear pair. That's what linear pairs do. By definition of a linear pair are two angles that are adjacent and are supplementary to each other. This was made out of thin air. You didn't need these other statements to make this one, but this one was made for the very reason that SRU is the brand new angle that we are going to be relating to both of these other angles previously. Now, what's going to happen here? Next statement. The next statement is the conjunction of statements 2 and 3. You can see that both sets of angles, both expressions are equal to 180 degrees, so we can set these expressions equal to each other. We can set PRS and VUW equal to PRS plus SRU because they both equal 180. That is two statements equal to the same, two expressions equal to the same expression or equal to each other. That is known as the transitive property of equality. And you don't see the step right here, but you can see that VUW still remains on this side of the equation. SRU still remains on this side of the equation. What happened was there was a measure of angle PRS on both sides right here. I'm going to subtract it from both sides like this. PRS. This is known as this is algebra. You do this all the time. Subtract something from both sides, and here it actually happens to cancel out. This is known as the subtraction property of equality, and this is an algebraic step right there. So we got these two things by themselves here. Now, something that I'd probably want to put in between as far as a statement goes, like a real statement 6, is that if measures are equal, then the angles are congruent right here. Just angle SRU. It's kind of better to talk about, because the same side exterior angles theorem states when those same side exterior angles are, when lines are parallel, same side exterior angles are congruent. And the converse is what we're going to be using right here, is that if same side exterior angles are congruent, then those lines are parallel, which is a true statement, for this particular instance right here. So hold on. So we found out that these two angles are equal. Well, hold on a sec. These aren't same side exterior. I'm sorry. We're talking about corresponding now. I'm sorry. So these two right here, we're talking about the corresponding angles right here. I mean, eventually we're talking about the same side. But these two are corresponding angles. That was statement 5 for those two angles here, VUW and SRU. Corresponding angles right here are congruent. By the way, if this statement was inserted in between, that would be definition of congruence again. Definition of congruence. If you had it inserted. Because corresponding angles are congruent, then these lines are therefore parallel. Let me check that again. Let me use a different color. If corresponding angles are congruent, then those lines are parallel. The corresponding angles postulate says if lines are parallel, then corresponding angles are congruent. Let's flip that and take the converse, which says if corresponding angles are congruent, then those lines are parallel angles. Sorry about that. Definition of corresponding angles. Sorry, this is a little bit messy for me to be talking about that. And that is your proof of what is called the converse of the same side exterior angles theorem. We just use the same side exterior angles theorem proof. Okay. Two more. Number 4. Now these are the ones where it's a little more complex in the sense that we can use alternate interior angles, alternate exterior angles, same side interior, same side exterior, and those theorems if we need to, because we're proving something of greater scope now, which is something. Some things that are a little farther out here. So, all right, here we go. Given that two different pairs of lines are parallel to each other, FH, this line right here happens to be parallel independently to this line, and then it's also parallel to this line right here. So we are going to be proving that angle RWX is congruent to angle STY. Now, when we look at where those are, RWX is right here. I hate looking for them in these letters. And STY is right here. Now, you might jump and say, these are alternate interior angles. They're congruent. You said that we can use that, right? Well, you have to be careful. These two lines aren't known to be parallel. I see a double arrow here. I see a single arrow here. They're not associated and known to be parallel here. I know that these two are parallel to each other. I know that these two are parallel to each other. And yes, we are now in a scope of something that we haven't yet proved and we can't use it, that two lines parallel to the same line are parallel to each other. That is not the transitive property. That's not a name that we can use for that thing. But we are going to build in to get to this proof right here. We're going to try and arrive at that eventually. So let's go off the givens. Let's see what we can use, and let's finally land on that answer when we get there. So we start with the givens that these two lines are parallel here. Let's try and understand this proof a little bit with each other. Angle STY is congruent to angle FGY. So STY is here, FGY is here. This one is the corresponding angles postulate right there. You can see that those two lines are parallel. Therefore, these two angles are congruent to each other as they are corresponding angles. So we can happily use that one. Now it looks like, now remember, FGY is neither STY nor RWX, which show up in the proof, but it relates to both of them in such a way that, let's see what FGY and RWX do with each other. They are congruent because FGY, where's RWX? Right here, because, hey, these are alternate interior angles. So what we're looking at right here, you're going to actually have to hide and ignore this other one for a moment, right? This one doesn't exist to us for a brief moment here. So this one is two parallel lines cut by this transversal right here. The middle line is irrelevant. Just look at the green only. You can see those are alternate interior angles, which can now be used in this scope. So we are going to be doing that, and those are congruent because of the alternate interior angles theorem. And two angles congruent to the same angle are congruent to each other. So let's kind of draw some of those arrows. Well, actually, no, let's not do that just yet. This is what's going to show up later. Two angles congruent to the same angle are congruent to each other by the transitive property of congruence. You can see the arc marks that therefore now show that these two angles are congruent to each other because this was congruent to this was congruent to that, so now this is congruent to that, despite the fact that the lines are not parallel. If I used one more step, I could use the converse of the alternate interior angles theorem, said when these alternate interior angles are congruent, then these lines are parallel, and that would have then proved that two lines parallel to the same line are parallel to each other. Now, normally I do the arrow drawing stuff, and I'm going to right now as far as answering these questions here. Which statement allowed us to arrive at statement 3? Meaning, statement 3 could not have possibly been built if not for which of the following statements, and just one of them. It's either this one or this one. It's only statements before it. Otherwise, statements after it would have been made before. So how can we say that STY is congruent to FGY? It was, let's see, STY was here, FGY was here. This happened to do with these two lines being parallel, SU and FH. SU and FH. That was because of statement 1 that statement 3 was possible. So here we go. Which statement allows to arrive at statement 4 that FGY was congruent to RWX? Here was FGY, here was RWX, and that was these two lines being parallel, FH and VX. So which one stated right here in statement 2, VX was parallel to FH? Because of that, we could make statement 4. So statement 2 leads us to statement 4 there. And finally, there were two statements that allow us to land on statement 5 right here. Statement 5 showing the transitive property of congruence, that again, two angles congruent to the same angle were congruent to each other. It's one of those bits where I'm sure you having the drawing allows you to make those statements for yourself, because we didn't have to make them for ourselves, right? This was already here. But because the statement is there, honestly, we don't need to look at the drawing anymore. What we need to say is, how was the statement built? Which was saying, well, this was congruent to FGY, and this was congruent to FGY, so I guess these two are congruent to each other, STY and RWX. Because of statements 3 and 4, we could make statement 5 right there. So 3 and 4. So that is the end of that part there. And again, that's really just the arrow drawing bits, and that's just a nice way to answer and bring that up. Okay, last one here. This one's going to be us fully building this one together. C marks on diagram for the givens. Now, we have to write out those givens that we see on the diagram as well, right? So there are a lot of connections we have to make. So complete the proof. This part that says use the drag and drop feature, stuff like that, that's stuff for my students, because what they have is they have the options on what's right there. I actually don't have them in front of me. I have no idea if they will follow exactly to a T what's written, so I hope they do. But here's an example of Mr. Robinson actually just doing a proof. So let's check this out right here. We are given single arc marks single arc marks to indicate, I was trying to come up with another noun, single arc marks to indicate that these two angles are congruent to each other. Now, I can't just call this angle P, because despite the fact it has really nothing to do with the diagram, this could have been angle P right here, this could have been angle P right here, we just don't know. So I have to be a lot more specific, and I'm going to be calling it angle SPT right here, angle SPT. So angle SPT is known to be congruent to angle RQT right here. Same thing there, RQT. The only angle here that I can call by a single letter is this angle S. So if I ever do, you might see me put that. Actually, I probably won't, because you can see here that says PST. So we'll just go ahead and call it PST whenever we can. Okay, so that is a given. It's given based on the markings. Even though it's not told, it is given based on the markings. We are also told, and shown with these arrows, these aren't congruent, but they are parallel to each other, that segment SP is parallel to segment RQ. Now again, I don't know if this is the order that they're written for my students, but that's totally true as well. Okay, I can't do anything off statement 1 just yet. I'm sure it's going to connect to something later, obviously probably through transitive property of congruence, but what we do have are parallel segments right here, or lines. I don't know if they put them as lines or segments, doesn't matter. But they're parallel to each other, and as a result of that, we can probably find some sort of, corresponding, whatever else. And what's going to happen here, because we're looking inside inverted triangles, is we're really going to be probably finding alternate interior angles. Consider these two lines that are parallel being cut by transversals here. I see a transversal right here. Hopefully you can see the same thing. I see a transversal right there in that line SQ. In that line SQ that creates, when these two are parallel, two alternate interior angles that are congruent to each other. And that's really what we're looking at right there. If you can see that in green, that two lines cut by transversals, alternate interior angles, ignore that blue line completely. We have angle PST congruent to angle RQT. We have angle PST right there congruent to angle RQT. Those are alternate interior angles that are congruent. Now that's because the lines are parallel. That's because of statement 2 that I could make that very statement. So that's the alternate interior angles theorem. Now, there are so many different ways you can do these things in order. It depends on what you want to do with it. I'm going to automatically draw a connection. Statement 1's right here, waiting in the wings, saying, when can I be of use? I'm going to go ahead and use it right now. Since we just found out that these two angles are congruent to each other by being alternate interior angles, you also know that this one's congruent to this one as well. So that must mean that these two must be congruent to each other, SPT and PST. Right? These two angles congruent to the same angle. So let's go ahead and bridge that gap right now and say, because of statements 1 and 3, and statement 3, by the way, was made because of statement 2. Because of statements 1 and 3, we can make a statement 4, which says that angle PST is congruent to angle SPT. I'm going to reverse that. Hold on. Angle SPT is congruent to angle PST, and that's by the transitive property of congruence. Now, this is not the only order that you have to do this, meaning the next statement I make could have been made next. It just depends on how you want to draw your bridge your gaps stuff. But I could have made this statement any earlier because I needed state by given. I needed my parallel lines to make this statement, and these two had to make that one. So that's the earliest I could have made this one right here. Okay, now we can do another set of two parallel lines cut by a transversal, the same set of parallel lines, but another transversal with another set of angles. So right here, these two can create, boom, alternate interior angles right there with those two parallel lines cut by transversal. That's SPT and QRT. SPT and QRT are going to be congruent to each other. Angle SPT congruent to angle QRT. And again, that's because of the parallel lines that we could state that. So that was statement 2 coming in the clutch again to make statement 5. Once again, the alternate interior angles theorem being done there. And, finally, we're trying to bridge that gap in how we're going to get to this QRT being congruent to PST. How are these two congruent to each other? Well, we can see the markings that we made to kind of lead to it. They all got the single arc mark treatment by being congruent to other things that were congruent to each other with those arc marks. But let's find out where they are statement-wise, and let's also call that, if we can, transitive property of congruence. But that's going to be angle QRT congruent to angle PST. So that was made by, let's see, QRT was congruent to SPT. PST was congruent to SPT. So both of these angles were congruent to the same angle. Therefore, they're congruent to each other. So statements 4 and 5 led me to statement 6. I know the arrows to you probably can't even tell what's being drawn there, but hopefully as you heard it, it made a lot more sense how it can be. Transitive property of congruence. Okay, and that's the last one. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I sure hope this was helpful for you, having that inner dialogue, how we mark things up, why we do, and how those things make sense. Thank you so much, guys. Take care. I will see you in the next one. Peace.